of it to individualized treatment effect. However, if you have seen parts of this talk a couple of months ago when I came and gave a talk in DAM, you will see that this talk is somewhat complementary because since then we came quite a lot further in understanding the theoretical underpinnings of causal inference. So today I'm going to mainly focus on that. Before starting, I'd like to thank my PhD students both at UCLA as well as in Oxford, especially my PhD student Mihaela, with whom most of the work that I'm presenting today has happened. But also I'd like to thank mathematicians and statisticians at our Turing Institute and a long and growing number of collaborators in the medical world without which this type of research would not be possible. So my research is focused on developing machine learning methods aimed at improving the quality and safety of healthcare while managing costs. And this work has two prongs. On one hand, we are developing machine learning methods to inform the policy perspective with the goal of developing guidelines, policies, and standards that are population serving and cross-sectional. And the second prong is aimed at assisting clinicians make better decisions, so developing clinical decision support systems and extract actionable intelligence from electronic health record data to provide clinicians with decision support systems that are personalized to the patient in front of them. These two perspectives are interacting with each other and interacting with machine learning. So the policy perspective is through the resources, policies, and guidelines that are provided for a particular healthcare setting, informing the clinical perspective. And the data that is gathered on the basis of this clinical perspective is used by machine learning to extract actionable intelligence that will inform further the clinicians, but also it can be used to derive and improve new policies for healthcare. Today I'm mainly going to focus on the second part of my research, which is focused on the clinical perspective and patient care. And the focus here is to use routinely collected electronic health record data, but possibly increasingly genomic data as well, to extract actionable intelligence to assist the entire pipeline of care, diagnosis and prognosis, screening and testing and treatments and interventions. And in order to do such research, we are very much involved with clinicians, medical researchers, but also with mathematicians and statisticians. Today, what I'm going to mainly focus on is how can we use this observational electronic health record data that is collected for a variety of patients to inform future treatments and interventions and enable to do personalization. In this area of clinical decision support, we believe that there is a long way that needs to be traveled, but the work that we have done so far is shown in here. On one hand, we have recently developed automated machine learning method that can be used for producing risk scores for many diseases. We are calling this framework autoprognosis, and it is an important framework because it enables us to automatize the process of risk scoring and enables us to not only compare one machine learning method and one statistical method, but a variety of machine learning and statistical methods are combined together to issue the best performance for a particular data set. Another thing that we have done quite a lot of work recently is looking not only at one risk, but rather at competing risks. So do time-to-event analysis where the events of interest may be correlated. So we have gone beyond existing methods such as fine gray or cost-specific Cox models and improved on top of them to be able to do time-to-event analysis for population that may have multiple morbidities. Another thing we have recently done is look at data that is collected in electronic health records, so when patients are going to see their GPs, and use this type of messy, regularly sampled data that may be actually very sparse to build disease trajectories and personalized disease atlases that can support clinicians in projecting not only risk for future disease and incident of disease for patients, but also to be able to identify what will be the effect of different comorbidities which their patients may have exhibited, or be able to project into the future different types of clinical biomarkers. So really, like we have a Google Atlas to inform us on how to navigate a city, the same, try to come up with a personalized atlas of the health of a patient in front of them. So it's a personalized atlas of disease. Some other work that we have done in the past, and I talked repeatedly about, is work on early warning systems in the hospital, but also this work can inform personalized screening policies. So we look very often at the value of information and the value of information over time. So rather than asking a patient to come back in 3 months upon, let's say, a particular diagnosis, try to identify when in the future the patient should come, 3 months, 6 months, couple of years, and what type of test should be acquired at that moment in time. So we look a lot at the value of information over time, and that's informed by the trajectories that we are learning. But we've also done some other work related to data imputation, especially data imputation over time, and also building recommender systems for clinical decision support. What I'm going to talk about today is our work on causal inference, and especially its application to individualized treatment effects. So the focus here would be learning individualized treatment effects from biased observational data as extracted in electronic health records. And if you look at current treatment decisions, they are often based on information that's extracted from control trials. And that can be at times not enough. So in many settings, it is well known that treatment effects for patients are heterogeneous. So often these clinical trials may involve only patients that are quite healthy, so patients that may not have multiple comorbidities, and often clinical trials exclude the elderly. It is still this population, the elderly and comorbid population, that's most of the time requiring these various drugs. So it is very important to not only upon the approval of a drug, we would like to understand which population especially is benefiting from this drug and which population possibly has a diminished effect or possibly even an adverse effect by taking this particular drug. So we would like to do what's called the post hoc analysis after a drug has been approved and it is in use. Try to look at electronic health record data and identify the subpopulation that is going to benefit from the drug and the population that may not. Even further, we would like to kind of issue individualized estimations of the treatment effects of different drugs for a particular individual. So the focus will be to estimate such individualized treatment effects of a particular intervention from observational data. And this work falls under causal effect inference as defined by Rubin. And it is related, but it is really quite different than causal relationship discovery as identified by Judea Pearl, my former colleague at UCLA. So our focus will be to use machine learning methods and think about machine learning methods in a very principled way to estimate causal effects for an individual by using observational data. And what we are going to try to do today is I'm going to develop some principled approach to think about this problem. So let me first introduce kind of the problem set up and what has been done so far. So in order to estimate individualized treatment effects, we have different types of observations, different types of features that are collected for the patients. And some of the patients may be control patients, some may be treated patients. And the focus here is really to estimate the treatment effect for a particular individual having a particular set of features. So the focus is to look at the difference of the outcomes, which we call the treatment effect, And the focus will be from the observational data to estimate the treatment effect. Note first that this is not a standard supervised learning problem. So unlike in conventional supervised learning problems, in this particular setting, we are not going to have counterfactuals. So let me define this a little bit better. So I have, for instance, an individual I or subject I that has a feature xi, and to which a treatment has been assigned. For instance, the patient is given a treatment or not. This can be generalized to more than 2 treatments. And what I observe is if the patient was, for instance, given a treatment, I observe that particular potential outcome, or if it was not given a treatment, I observe the other potential outcome. So I do not observe both of them at the same time. So I only observe the factual. The counterfactual is not observed. So unlike in a conventional supervised paradigm in which I can easily test out of sample, in this setting I cannot do that. I cannot say, well, what would have happened if I would not have done this surgery on this person? I've done it already. So we would like to issue estimates for our predictions, but also it's very important in this setting to issue confidence associated with these estimates. And depending on the confidence, the decision by the doctor may be to follow the advice or not. So whatever predictions we are and estimates we are developing cannot be tested in the standard paradigm of supervised learning. It's a lot harder problem. And another important problem is that of bias. So the doctors, fortunately for us, the patients are not closing their eyes and deciding whether they should do a surgery on us or not, or give a particular drug or another drug. They are informed by some of their own judgment. So on the, I should say, on the negative side from the machine learner point of view, from the patient point of view is positive, but from the machine learner point of view, the patients are not assigned to treatment randomly. So there is bias in the data. We need to deal with this bias. On the positive side for the machine learner, there is a chance to learn because different treatments may be assigned to similar patients. So we need to learn on the basis of a biased data set which doesn't have the counterfactuals. So we are casting this in the well-known model of introduced by Neumann and Rubin, which is making several assumptions. So again, let me remind you, I have an individual I which has features xi, I have 2 potential outcomes, and I have a particular treatment assignment. I just observe the outcome for the assignment, not for the counterfactual. And this is the propensity function associated with the data set that I have. The 2 assumptions that are made in this literature are, on one hand, the fact that the potential outcome will depend on the features of the patient, but not on whether the patient was actually treated or not treated. So in other words, we are assuming no hidden confounders. There is no hidden confounder that was available, the information is available to the, let's say, clinician, but it is not recorded in the data set. So that is an assumption that is made in most of the literature. Another assumption that's made is that of overlap, and that means that there is no array of features for which either all the patients were treated or all the patients were not treated. So we have the opportunity to learn. And the focus is to learn individualized treatment effects. So for a patient with this particular array of features to estimate the treatment effect. There is a lot of interest in this area of causal inference dedicated to individualized treatment effects. Many communities have worked on it, which makes it especially interesting. So work that has been done in recent times in statistics, in econometrics, again in statistics, but also machine learning. So a variety of methods have been developed recently that span a variety of ideas and methods. And I'm going to discuss the relationship of the theory that we have provided with this work a little bit later. Let me start by saying that most of the work that I described in the previous page can be classified in two main areas. In the first set of methods, the idea has been that they have divided the two models of treated patients and untreated patients as two separate models, and they have learned regression models associated with them. So this is a very simplistic way, to some extent, to deal with this problem. Fit a regression model for the treated, or it could be not, it doesn't need to be a regression model, it could be fit some type of machine learning method to the treated, fit some other model to the control population, and treat them independently. In this way, if you don't have a lot of observations, you are also going to suffer due to the statistical inefficiency associated with splitting your data in two. You are not able to share, to learn across the populations, but this will be a particular method. And actually, I'm going to show to you, and you will see that it is quite surprising that in some settings, these methods are not doing horribly, as you may expect. And there are good reasons for it that I'm going to come later. The majority of works, though, falls in this other category, where the treatment is just viewed as an additional feature. So these are the patient features, and these are the treatment is viewed purely as another feature. So the space of features is augmented with another input. And many techniques, most of the techniques in recent times have been that have been proposed fit in this area. And what I'm going to try to show with our theory is that unfortunately these methods are always going to be suboptimal for the causal inference problem. So we need to really think in a different way about this problem. So a limitation of the existing methods is that many of them have treated this problem of causal inference as yet another machine learning problem, yes, which has bias, but less counterfactuals, but without a specific special modeling for that models the unique characteristics of this problem. Often the methods are suffering from modeling specification. Some of the work has some measures of uncertainty, but the majority of it does not. So it issues predictions without uncertainty estimates. And there is absolutely no theoretical foundation for thinking about causal inference with respect to individualized treatment effects. So we don't know what are performance limits. What can we achieve really in the limits? So what we are trying to propose here is a framework that we are just starting to build on, which is going to use a Bayesian non-parametric model. And the reason we chose that is, on one hand, we are going to have flexibility, we are going to be robust to modeling specification, we are going to be able to issue uncertainty quantification. And through the work, through our relation of this work to information theory, we will be able to provide some theoretical guarantees and be able to reason about what methods, how to think in a more principled way about developing methods in this area. So what I'm going to do is I'm going to start by talking about some of the theoretical results that we have developed in the last couple of months, where we are trying to establish fundamental limits for causal inference from observational data. Then I'm going to use these insights to talk about how to design practical algorithms, and then I'm going to show some results. So just a brief preview of results. Our approach, as I mentioned, is going to be a Bayesian non-parametric model. We are going to establish first, using information theory, an equivalence between Bayesian information rates and the frequentist estimation rates that are often used to estimate and quantify the performance of these causal inference methods. Then we are going to characterize the optimal information rates that can be achieved by any Bayesian non-parametric learning algorithm. So this is, if you like, what's achievable by any algorithm. And then we are going to see, can we use this knowledge to identify classes of algorithms that are informationally optimal. So, as I mentioned before, we have access to two types of information, control and treated population, and what our focus is on estimating these treatment effects. And a question that we would like to answer is, how well can any estimator do? So we would like no longer to look first at algorithms, we would like to pose this more like an information theoretic question and see what are the fundamental limits of this. So how hard is this problem? And we are going to try to attempt to answer this question using information theory. So we are going to use a Bayesian approach, and we are going to put a prior pi on the response surfaces. We are going to make very standard assumptions about this prior. And what we are going to define is a notion of risk for this prior pi with respect to the observations, the outcomes, and the propensity. And we are going to do that in terms of the KL divergence. So this is going to provide us a notion of risk, which we are going to use as the core metric to identify or to define the information rate. So we define information rates in the context of this causal inference problem as the asymptotic equivalence class of this KL risk. Then a first theorem is establishing a relationship between this notion that we have identified of information rates and what currently is used for benchmarking the different algorithms on causal inference, which is a frequentist loss that is called PEHE, which stands for Precision in Estimating Heterogeneous Effects, which is work done by Jennifer Hill in 2011 and represents the current way in which the different algorithms are benchmarked against each other. So it is this frequentist loss, which is used for benchmarking, that now we identified a relationship to the information rate. So in other words, what this theorem is saying is that a good information rate, which is bounding this KL risk, will lead, if we have such a good information rate, then we are guaranteed to have fast convergence of that. So really, what does it mean to have optimal information rates? Well, this information rate, we have defined this information rate of a prior given response functions. But the trouble is that we don't know the response functions. They need to be learned on the basis of the data. So what if we only know not the response functions, but the classes to which these response functions may appertain? So, for instance, we can have alpha smooth functions. We could have Lipschitz functions, and I think thinking about Lipschitz class of functions would be a good one, but you could have more sophisticated, you could have Sobolev, or you can have Holder class. You will see most of the results actually in our work can be derived for a very general class, but the expressions can get very ugly. So a lot of the results that I'm going to put on the slides, not to scare anybody, are going to be actually for Lipschitz, for the Lipschitz function class. But they could be defined very generally, and we are going to assume that they are going to be in some type of alpha smooth class. So given that, we are going to define this optimal information rate as a Maximin approach. So we are going to define the achievable information rates as the worst case information rate. Note that these are information rates, so the lower the better. Yeah, so this is actually a min, and the optimal information rate will be a max-min. So we are going to determine the priors that are going to maximize this achievable information rates. So this is what we are going to try to go after. Note also that the optimal information rate is again a property of the function classes, and the function classes to which potential outcomes functions belong. So it's a property of those function classes, and it does not depend on the inference algorithm. So the key idea is really that in order to determine these optimal information rates, we would like to say something about the size of the function classes to which these response functions belong. And the smoother the response functions, the happier we are, because the smaller function subspaces, and the better the information rates. So one example could be the Lifshitz space. Informally, if you want to think about this informally, the size of a function class is really measured by how big a finite set we need to choose to be assured that the approximations of every function potential outcome in that class can be well enough approximated. Formally, what is this is nothing else than the covering number. So we are going to work, though not with covering number, but we are going to work with something that's much more common in information theory. So that's the logarithm of the covering number. So I'm much more used to that, and we are going to work with metric entropy. So we are going to use these covering numbers and convert them to the metric entropy. Just to give an example, this is the metric entropy for the Lifshitz function class. And notice here, for instance, the larger D is, so the more features I have, the larger the metric entropy, unsurprisingly. On the other hand, the smoother, the less smooth the functions are, the larger the metric entropy, the bigger trouble I'm going to have to approximate these functions. This is a picture to kind of give you an idea about what's happening. So let's assume that I would like to approximate function classes with, let's say, up to delta. And I have here the control response function, and here I have the treated response function, the two spaces. And what you see is that usually they don't have the same smoothness. The treated and the response surface have different smoothnesses. And it is quite common that the control response surface is smoother than the treated response. It doesn't need to be the case. It could be vice versa. But usually that's the case. And what you see here is really the covering number and the metric entropy associated with these two function classes. Then a second theorem is identifying the optimal information rate. And we have general formulas for alpha smooth functions, but here I'm just showing you one for the Lifshitz class, function class, because the other ones look really ugly. You can see them in the paper. But I think that this is enough to understand some of the key insights we can get from this type of theorems. First, I like to say that these exponents here are coming from the metric entropy for the Lifshitz function class. So what can you observe on the basis of this? Yes, we can identify the optimal information rates, but what does this really mean? The first thing that's interesting to see is that selection bias does not matter. These optimal information rates are independent of the propensity. A second thing is that the optimal information rate will depend on the larger function class. So it depends on the rougher response surfaces. So they are the ones that are going to determine the hardness of these problems. Let me draw some connections, since some of you are statisticians, with well-known and wonderful work on optimal kernel density estimation. This is a different problem, but it has some relationships, and it's interesting to draw these parallels. So what we have just proven is that the selection bias does not affect, in our case, for causal inference, the optimal information rates. This is related, if you like, or is, one can draw this parallel to results that exist in minimax optimal kernel density estimation under bias, when the data is biased, from biased data. So we know that in such settings, the selection bias does not affect the optimal minimax rate. So this is interesting to see this parallel. Also, we know from the theory of optimal kernel density estimation that while this is not the case, if you now want to build optimization strategies for kernel bandwidth estimation, then you do need to take into consideration the selection bias. So when you try to make achievable, yeah, it's like information theory, very often you have bounds, but also then you try to develop algorithms that are bringing you to these bounds. As soon as you start to think about real algorithms, you need to start to worry about selection bias. And indeed, you are going to see that we ourselves, as soon as we are going to start to try to achieve these optimal information rates and information theory bounds, we will need to worry about selection bias as well. So before going there, let me say a few more words. So what I did so far is I assumed that all the features are relevant to be able to estimate the optimal information rates, but this may often not be the case. It may be that only a subset of features are relevant and are informing the treatment outcomes. In that case, one can prove that the optimal information rate can be tightened. It just depends now on these relevant features. And after some algebra, two key insights can be derived. One of them is that the optimal rate depends on the complex or the most complex response function, but also that the surface with a smaller smoothness sparsity ratio is the one that's going to decide, is going to dominate and decide the optimal rate. So informally now, let me visualize what this means. So on one hand, we will need for a prior pi to achieve this optimal information rate to be sparse. So pi needs to account only for the variables that are relevant. So we need really to determine and select a pi when we are going to construct algorithms that ignore the irrelevant dimensions. And the second thing is smoothness. So we will need to choose priors that place high probability on sample paths that match the regularity of the rougher of the two surfaces. So we don't want to have undersmooth or oversmooth. We want to be able to build algorithms that select priors which are matched to the rougher of the two surfaces. So these are two criteria that you are going to see being used in determining what classes of algorithms can provide us the optimal information rate. So a natural question that arises is we know what the optimal information rate, but how to get there with algorithms. So how can we achieve that? As long as we select from a class of priors fulfilling several properties, inclusively posterior consistency, we can determine what are smoothness matching conditions for these priors. What type of priors will be able to achieve these optimal information rates? And let me try to kind of read this theorem. This theorem, what it says two things: that the optimal rate is achieved only if we are able to match the rougher of the two surfaces, and we don't do something too bad for the other one. This is roughly what this theorem is. So how does this relate now to the algorithms that have been developed so far? The algorithms that have been developed so far that are using treatment as a feature. So this is this example which is using the second class. Most algorithms that are developed in the last couple of years follow in that class, where the treatment is used as a feature, is augmenting the other features. So it does not have a special role, it's just yet another feature. I'm going to call this type 1 prior, and most of the methods fit in this category. And the trouble with these type 1 priors is that it restricts the smoothness of the response surfaces. So this also entails that the relevant dimensions for the two response surfaces, treated or untreated, need to be the same if you are constrained to choose from this type 1 prior. So if you restrict yourself to this type of methods, like have been developed so far, which does not allow for the treatment to be viewed differently and to construct algorithms in a more flexible way, the performance is going to be significantly impaired. On the other hand, if you allow the treatment assignment to index the different models and you select priors correctly, there is hope that you can achieve the information rate. And I'm going to show to you how one can develop methods based on this category of insights to achieve optimal information rate. So first, for this type of methods, one can write a formal result showing that this type 1 priors can really not achieve the optimal information rate, while type 2 priors can achieve the optimal information rate. But it doesn't say how, it just says that it's possible. So now we are going to try to pursue how to do that. And we are going to start to think about designs that will hopefully bring us towards that goal. So for that, we have developed a method that is using these Bayesian non-parametric methods, but which selects priors that are reproducing kernel Hilbert spaces. And this beta is the smoothness parameter associated with it. So we are going to model the potential outcomes as a vector-valued potential outcome function. And these surfaces are going to come from this reproducing kernel Hilbert space. And what we are going to try to determine is what type of priors we should put on this vector-valued space, such that we can achieve these optimal information rates. So let me first say what is really this beta parameterize, how it really parameterizes smoothness. It is doing so because this covariance kernel function will be able to control the smoothness. Yeah? So for instance, if I'm using Gaussian process priors, I could use something like a Matern kernel with a parameter beta that will control the smoothness of these function classes. So these Gaussian process priors then, if I choose them correctly, if I choose a prior on this vector-value reproducible kernel Hilbert space, that is going to select a multitask Gaussian process. And suddenly, by selecting these priors and using the observational data, I can compute posteriors over this vector-value reproducing kernel Hilbert spaces. And in effect, what I'm going to be able to do is, I have these posteriors over the potential outcome distributions, which now I'm going to be able to convert into determining uncertainty, individualized uncertainty estimates for my treatment effects. Let me talk about how to do that. So recall first that in order to attempt to achieve the optimal information rates, I would like to achieve two things. This is a recollection of the prior results. One of them is I'd like to choose these priors in such a way that I have sparsity, so the prior is defined only on the relevant features, and I have smoothness. I can match the smoothness of the rougher of the two surfaces. So key to achieve this is two steps that I need to use to develop such algorithms for causal inference. First, I can build a GB kernel that allows for incorporating for both smoothness and sparsity, and then design some type of hyperparameter optimization method, some algorithm that is able from data to uncover the smoothness and sparsity. So how do we do that? So for that, we are using this multitask GP kernel for the treated and the control population. And this multitask GP kernel will assign separate hyperparameters for the different surfaces. And hence, this enables us the flexibility these type 2 priors have and type 1 priors do not, to capture the relevance and smoothness for the different surfaces for every dimension. We are doing that by using kernels which are linear coregionalization models, where I have these two kernels, one for the treated, one for the control, and then I can use automatic relevance determination to determine what the features that are associated with it. So I can do quite easily variable importance, and this can be done quite easily in these GP models. The second part is trickier though. How do I recover the smoothness? And I need to recover the smoothness in a careful way because I need to fit, in order to have optimal information rates, I need to match the conditions that I was proving in the theoretical part that preceded this. So I need to recover in such a way that I match the conditions necessary. So this is trickier because selection bias may affect the smoothness recovery. So unlike the optimal information rate may not care about this, but when you develop algorithms, you need to deal really with this bias. And also, secondly, this hyperparameter optimization, if you are just doing some type of likelihood optimization, may not work. So this is why thinking in this Bayesian non-parametric way will be very useful, because now I can define a Bayesian risk as a proxy for the true estimator, the true estimation error. And I'm trying to highlight this, what is happening. So I have, for instance, treated and untreated factuals, but I'm going to estimate for posteriors the counterfactual outcomes. So this Bayesian framework will allow me to have estimates of the counterfactuals through the posteriors. So now I can estimate the Bayesian risk, and I can estimate the variance of the counterfactual, which reflects the selection bias that's in the data. And I can use that now to recover the smoothness using the Bayesian risk. And I can match the conditions that I need. So a result of that insight is that in order to have an optimal performance given my data, I need to select parameters, hyperparameters that are going to minimize this expression. And what is this expression? So this is aiming to minimize the empirical bias risk. And the result is actually quite interesting and quite interpretable. So what it says is that these hyperparameters need, on one hand, to minimize the empirical factual loss, but at the same time, they need to also penalize and minimize the posterior counterfactual variance. So if you look at a lot of the existing literature, is very much focused on minimizing the empirical factual errors, but not dealing correctly with the counterfactuals. If it is to kind of bring these insights from let's say, Bayesian on parametrics to machine learning, very often in machine learning we are thinking about representations and learning representations, and there is a nice duality between the two of them. So this vector value reproducing kernel Hilbert spaces on features are nothing else than linear function spaces, representations that one can learn in the feature maps. So on one hand, what this previous theorem is saying is that we would like to learn as good as possible representations for the factors, while making sure that the posterior distribution of the counterfactual is also minimized. Okay, so now that we've done all this, so let's look at the evaluation of the model. And for that, we are going to use the standard framework that is used in Causal Inference, as introduced by Jennifer Hill. So since we don't have at our access counterfactuals, we are going to generate these counterfactuals in the same way as the literature is doing. We are going to create semi-synthetic data sets where the outcomes are simulated. So we are using a very standard data set that is used for this literature, and this is a data set that is based for infant health development programs. So it's a data set that's based on actually on a randomized controlled trial which is made, it's transformed into a biased data set by Jennifer Hill. So what we have is we have nonlinear synthetic outcome models as generated by her, and the relevant variables are randomly determined in each experiment, as it is done in this literature. And we are going to average results over 1,000 repeated experiments, as often done in this work. We are going to compare to a variety of methods that have been compared also on this specific data set. Again, some of these methods are coming from statistics, some from econometrics, some from machine learning. I'm also, as a sanity check, I'm going to put the propensity score matching just to have another benchmark. Of course, both our method as well as these methods are focusing on individualized treatment effects, but still it would be nice to understand how well propensity score matching is doing. In addition, I'm going to also compare with the first set of methods, which is not modeling treatments as a feature, but is splitting the factuals and splitting the treated and untreated as separate response surfaces and fitting to them separate models. So I'm going to compare against a variety of methods ranging from Gaussian processes to random forest to boosting algorithms to state-of-the-art deep learning methods. And here are the performance results. Let me start by saying that this is the PEHEC. Yeah, so this is the measure of error for the causal inference methods. The lower, the better. So the smaller value, the better. What we need to focus on mainly is the out-of-sample PEHE. I'm also reporting the in-sample PEHE partially because in some settings this has been reported as well. But it is the out-of-sample PEHE that is the most relevant. And what you can see here is a couple of things. So first you can see that the method that we have developed on the basis of this theoretical understanding of this problem is really doing quite a lot better than anything else. A second thing you can see here is that actually the causal Mars method developed at Stanford by a collection of researchers in statistics and the medical school is the second best method. But what you can also see, but it's quite far away from what we can achieve. Another thing that I think quite interesting is I had expected when I started this exercise that the methods that are splitting the data in two are going to be really very bad. But you can see that some of them, like for instance, the boosting algorithms, are actually not necessarily that bad. So, and some of them may be even better than some other methods that have been developed on purpose for causal inference. Okay, now a final word I'd like to say, we would like to apply such insights on the basis of real data as well, and try to understand whether it can be useful in practice to guide clinicians in making decisions about treatments. Of course, this is something that's still ongoing and one needs to be very careful about. So what I'm showing to you now is more like work in progress and early work in progress, I would say. But we have tried to use this to identify whether treatments that are given to a certain subpopulation of patients that have cystic fibrosis would be beneficial to some and detrimental to some others. And we have a long-standing project on cystic fibrosis that actually we started 7 months ago, but we hope it will continue for a long time. And we look at different aspects of the cystic fibrosis population. And this is especially interesting because it's a very complicated disease. And since patients die at a relatively young age, it is a work that really is every life that's saved is very, very important. So we would like to understand whether these treatments that are given to cystic fibrosis patients are possibly more effective on some population than others. And again, this is important because many of the clinical trials for cystic fibrosis enroll very few patients. And we have applied this to a drug that has been hailed as being the most important new drug of 2012. It's Ivacaftor. And this is the first drug that treats underlying cause rather than symptoms. And after clinical trials, really is routinely prescribed to all CF patients with this particular mutation. And our goal has been to see whether we can identify treatments, subpopulation for which this drug is working better or worse. So what we can see is that while for the majority of the population seems to be working indeed quite a lot better, is going to make the patients better, It has little or no effect for patients over 30 and patients that have bacterial lung infections. And based at least on our current analysis, and of course we need to be very cautious, this is again work in progress, it seems that ivacaftor has negative effects for patients that have cystic fibrosis-induced diabetes. And this work is continuing, and we need to spend a lot of time and energy to understand what is happening. This is not just a risk prediction, you can apply it out of sample and validate on a totally new population. Here we cannot do that, we cannot do this on the population that is given or not given this drug. So we need to be really going back to the biology of it and really try to understand whether these findings indeed make sense. And this is work that is now ongoing. But I think that this is an important problem because currently ivacaftor costs $300,000 a year, and it is given to patients that are very sick. So we need to really ensure that this drug is effective to the population that is given. Overall, I feel that the work that I presented on causal inference can serve as a wonderful complement, not as a substitute, but as a complement to existing work on randomized control trials. Again, randomized control trials are usually expensive. They enroll population that is generally healthy. The elderly or population that has a lot of comorbidity is often not enrolled. So complementing that using causal inference for post-hoc analysis is a very important task. Also, potentially, this can be used as recommender systems for clinicians to consider one drug or another for the patient in front of them. And finally, in the longer term, possibly can inform current information that we have about subpopulation that may benefit from a particular drug, can inform development of new drugs as well. Or vice versa, if a particular drug is not very effective in a population, then maybe new drugs can be targeting this population rather than the general population. Here is some of the work we have done in this area. The theoretical work that I presented here, it's in the archive and it's currently submitted under evaluation. And some of the algorithms that were inspired by this framework are presented here. And the algorithms are actually quite diverse. Some of them are building directly on the method that I described here. Some others are using some new form of deep learning methods based on generated adversarial networks and trying to use them for individualized treatment effects. And this is my last slide. So it is really my belief that machine learning can play an important role in not only informing the treatment of patients, like described in this talk, but more generally can assist clinicians to extract actionable intelligence, to provide them with more information for the patient in front of them. By no means to replace clinicians, just to provide them with information that they can use to make decisions. And conversely, as these doctors are making decisions and are using this information or not, that can be taken into consideration and improve these methods such that they can be of further assistance and they can be improved. I also believe that this can influence clinical research because associations between features can be extracted and uncovered through the help of machine learning, and especially with the whole new world we are nowadays having, where we don't have only electronic health record data, but also omics data. It's really a very exciting time to really use all this information, extract all this information to help clinicians make better decisions for individualized, for the patient in front of them. Thank you very much.
We've got time now for a couple of questions or comments.
The infectious diseases sort of work by J.D. Robbins and Stephen Cole McGowan sort of dominate a lot rather than these sorts of methods. And the closest thing that I saw in your data comparison was Mark Vanderland's targeted MLE sort of stuff. I wondered whether you had an idea of why those different methods are not performing as well as yours. Well, I understand that you're trying to, everyone's trying to do the sort of thing in terms of sparsity and smoothness. I wonder whether you could say, based upon your theory, why you're doing so much better.
So I already kind of tried to say that when I talked about these different priors. So a variety of these existing methods are treating this, are treating treatments not as a parameter that needs to be used to select, let's say, the shape of the factuals and counterfactual outcomes, but more as a way to kind of split the data or learn on the basis of the data. So that can lead to not effective way of dealing with bias. So for instance, one of the things that I showed was that by selecting hyperparameters correctly on the basis, not only on the factual outcomes. So a lot of the existing work focuses on fitting as good as possible the factuals. And when it comes to the counterfactual, either it's ignoring it or is using average treatment effects, or it cooks up some type of cost function, rather than in a principled way try to identify what would be optimal priors that are really fitting this empirical risk, if you like, that are minimizing this empirical risk. So I would say the answer is twofold. First, we already showed that type 1 priors are never going to achieve. So as long as treatment is viewed as a feature, you cannot hope to achieve a very high performance because you're lumping everything together. Then if you're in a second category, and I would say very few methods exist in the second category, but if you're in the second category, then you need to go one step further. You need to really, have the flexibility to control these two surfaces. But you need to do that in a way that's principled. If you just are penalizing, let's say, in an ad hoc way, the representations when fitting them to the factuals, you are going to not consider in a principled way the impact that you are having on the counterfactuals. I'm not sure. This is, I think, the work that I presented here is a kind of a first attempt to try to understand this. Why? So when we published our first work in NIPS, we were seeing these performance results that our method has provided. And actually, I presented it in DAMP, that research even as soon as actually the paper got accepted, I actually came here and gave a talk about more about the methods. But at the time, we were ourselves very happy with our results. We had some understanding, but not a theory behind it. So the attempt today was to kind of provide some of these principles using information theory to try to understand what is an optimal performance in this setting. So I would say a criticism to the existing literature is that it tries to think about this problem only algorithmically, rather than trying to really understand what could be achieved optimally. But I think a lot more can and should be done in this area. I think our work is just the very beginning of a lot more work that is happening. And definitely the work of Van der Laan is very important in this area. And a lot of our proofs, let's say, use concentration bounds and work that he has developed.
I actually have a follow-up question to the previous one. The numerical results, I have to say, is a little bit too impressive to me. And I'm just wondering, is it possible, because you use the same set of data, you learn the sparsity, you learn the smoothness, and you fit in the end. Is there a danger of overusing the same set
No.
of data?
No, so these tests, so first we are using the same data set as everybody is using. So in this community, almost everybody is using this particular data set and is averaging over 1,000 experiments. These are out of sample results. They are not in sample results. So none of that is there. Again, I would like to emphasize that unlike the existing literature is quite ad hoc. For instance, at times people are fitting BART or causal forest or splitting the data. There is a very much inefficiency in this type of ad hoc modeling. Yeah.
What is the theoretical threshold for the PhD for this data set?
how far can, as you probably know from information theory, it is very, how far can one get for a particular data set is by itself a very hard problem. So how far can you go? We
If
don't
you
know.
plug in your smoothness estimator, your sparsity estimator to the threshold.
But you still may not be able to determine how far can somebody go. So again, like in information theory, very often for source coding, for instance, one can give you a data set, not a class of a model, but rather a data set, like in this case. And if you ask yourself how far was the limit, or the source code limit of this, we don't know that. Similarly here. So the fact that we have a distortion theory, or that we have here an information theoretic way to do it, it doesn't mean that if somebody gives you an empirical data set, you are able to compute how far can you go.
Just a question out of curiosity. So it's on your last slide. It's more philosophical question. You separate these steps, so the genetic associations and the causalities. But
oh, I shouldn't. I should
yeah,
not.
wouldn't
definitely. Oh, definitely. No, no. It's just an artifact of trying to plot many dimensions. It is clear that this is very much influencing that, and of course, I'm aware of alternative ways.
yeah, but I think this is still the way it's been done very often. I mean, people do variable selection using association studies, but we might have the wrong variables, right? And that's,
Definitely,
yes.
definitely. So actually, part of what I've tried to present here goes a little bit in the direction, because we are saying we would feed in. I'm not saying that we have done this for genomic information, but we feed in all the information we have from electronic health record data, for instance, for this data set that we have on cystic fibrosis. And we let the data kind of speak, so we identify which parameters are, which features are actually the relevant ones for the treated and for the untreated. So we are learning that on the basis of the data.
But I could argue that for genomics, you probably, I mean, your function space is very large, and for genomics, you probably need to use a very simple function space because your dimension is so huge.
Yeah. But I think that's a lot of interesting work that needs to happen. So I agree with you. I think that there it's a lot more complicated, and it's wonderful work by Candace and others going in that direction. And I think it's exciting, and I hope a lot more work will happen. And by no means I'm saying that it's a small begin. To try to really encourage the community to think more deeply about how to think about these problems. And information theory may not be the only way to think about this and formalize it. And as we were discussing, information theory at times can give you some type of way to think about this problem, but it doesn't mean, as I was mentioning, that somebody gives you a data set you can compute. What would be the distortion of that particular, or in this case, would be the information rate for that. We very often cannot do that. That's the frustration of being an information theorist. Yet, it is wonderful that you have a way to think about problems, because it can inform your algorithms. And at times, like in channel coding, one may come up with methods that are really matching those making these bounds computable. So I think it's an exciting area.
Okay, I think that's a good point to leave it. So let's thank Mihaela again for a great talk.
Thank you.